Hello everyone. Today's talk is on the fractional knapsack problem based on greedy design. What is fractional knapsack problem? Given a knapsack or a simple bag with a set of objects named as O1, O2 and so on till On, with the weights of the objects named as W1, W2, W3 and so on till Wn, and the profits of these objects given as P1, P2, P3 so on till Pn. The aim of the fractional knapsack problem is to obtain a filling of this knapsack in such a way that the total profit of all the jobs put together is maximized without exceeding the bag capacity. You're given the bag capacity as C. So when we select objects and put them into the knapsack, we have to keep in mind that the total profit of the items or the object selected is maximized under the constraint that the bag capacity is not exceeded. This is a very popular greedy design problem, and it belongs to the maximization case of optimization problems because the aim is to maximize the profit. Now, this problem is called as a fractional knapsack problem in order to distinguish it from one other variation of the knapsack problem called as 0-1 knapsack problem. The 0-1 knapsack problem is yet another knapsack problem variation in which if we find that an object's weight exceeds the bag capacity, we have to reject that object. Or in other words, in 0-1 knapsack problem, if an object cannot be accommodated into the knapsack or bag, then we are left with only rejecting that item. Whereas in the fractional knapsack problem, if we find that an object cannot be accommodated into the bag because it exceeds the bag capacity, we have the option of taking a fractional unit of that item or object. Or in other words, we could split the item and pick a fractional unit of that item and put it into the knapsack. Now, the fractional knapsack is based on greedy design or solved using greedy design, whereas the 0-1 knapsack, the most efficient way of solving the 0-1 knapsack is using the design technique called dynamic programming. Now we formally define the greedy knapsack or otherwise a fractional knapsack problem. Now consider that we have object OI, we have an object OI, and assume that xi is a fractional unit of the object OI. So if I choose a fractional unit xi of an object OI, whose weight is wi and profit is pi, then profit generated for that particular object would be xi into pi, and the weight generated would be wi into pi. Given that xi is a fractional unit of the object OI selected, with its respective fractional unit as xi, then the profit generated is xi into pi, and the weight generated is wi into pi. Now, if I formally state the greedy knapsack, it satisfies these two conditions. The first condition that it has to satisfy is to maximize the profit of all the xi units of the object selected, where pi is the respective profit. So suppose I consider there are 3 items to be selected, then x1, x2, x3 would be the fractional units of the objects 1, 2 and 3. And P1, P2, P3 would be the profits of the objects O1, O2 and O3. So the aim is to maximize the total profit of all the 3 items 1, 2 and 3. Hence it is defined as maximize xi into pi for all the items ranging from 1 to n, where n is a total number of items or objects. Maximize the profit of all the items selected, subject to the constraint that the total weight of all the items selected is within the bag limit C. Now you can consider Xi as a fractional unit of an item selected, and the fractional unit always varies between 0 and 1. Given such a formal statement of the greedy knapsack problem, we could define what are feasible solutions and what is an optimal solution. All solutions that satisfy condition 2 are said to be feasible. They are feasible because I could pick up any combination of items I put into the backpack. All of those combinations of items picked would fall within the bag capacity C. But the aim is to pick one such feasible solution or decide on one such feasible solution that satisfies condition 1, which is nothing but maximizing the profit. And such a solution, I call it as an optimal solution. So all solutions that satisfy condition 2 are said to be feasible because they do not dissatisfy the problem constraint. So all such solutions are said to be feasible. Any one feasible solution that maximizes the profit is said to be an optimal solution for the greedy knapsack or the fractional knapsack problem. So what could be the possible solutions, or what are the different ways in which we can find an optimal solution for this problem based on greedy design? One of the first and most obvious choices would be to select the most valuable object always. Since I'm following a greedy design, I choose to select the most valuable object at every stage of the problem. The second method would be to select the most lighter object always. So when I select the most lighter object in every step, I would end up adding more number of objects, and hence the aim would be to maximize the profit. So the first case would be to select the object with the highest profit or the most valuable object always. And the second case would be to select lighter objects at every instance, thereby adding more items into the knapsack, and hence maximizing the profit. Now we find that both strategy 1 and strategy 2 does not always result in optimal solutions. Hence, the best method to generate an optimal solution for the fractional knapsack based on greedy design is to select objects which has the highest profit by weight ratio. Or in other words, I have to order all the objects or items in the descending order of profit by weight. Pick each item in such a way that it maximizes the profit while minimizing the weight. In doing so, I would also be maximizing the profit and taking more number of items into the knapsack. Now, such a solution which picks items with the highest P by W ratio would give an optimal solution to the fractional knapsack problem. Now we go on and see a very simple instance of the fractional knapsack problem. Assume that the bag capacity or the knapsack capacity is given as 100. The objects are O1, O2, O3, O4, O5. The weights as 10, 20, 30, 40, 50, and their profits are given. The first step towards building the solution using greedy design, as we discussed earlier, is to find the profit by weight ratio for each object. So it would be 20 by 10 for O1, 30 by 20 for O2, and so on. So I would just write this as D4 by C4. So I have just determined the profit by weight ratio of all the objects. Once the profit by weight ratio is determined, the next step is to order these objects in the descending order of profit by weight ratio. So if you look at these objects here, or the P by W ratio, 2.2 is the highest. So O3 is ordered first with 2.2. Then we order O1 with 2. Then we order O2 with 1.5. Then we order O5 with 1.2. And then we order O4 with 1 as the P by W ratio. First step of the solution is complete. We have determined the P by W ratio and then ordered them in the descending order of P by W ratio. Now we move on and find out which are the items that should be picked and what unit of these items have to be picked to generate the maximum profit. Since we know that O3 has to be picked up, we find out what is the weight of O3. The weight of O3 is given as 30, and we know that the bag capacity is given as 100. Please note, the bag capacity is given as 100. Now, the maximum unit or the maximum amount of the object O3 that I can select is 1, because the weight of 1 unit of O3 is 30, and 30 can very well fit into 100. So I can decide that I can select 1 unit of the object O3, and hence the profit generated at this instance would be 1 into 66, because 1 unit of the object O3 generates a profit of 66, and 1 unit of the object O3 selected generates a weight of 30. So what would be the remaining capacity? This would be 100 minus 1 into the weight, which is 30. And hence the remaining capacity after selecting object O3 into the bag is 70. We move on and pick the next object O1 with the next highest P by W ratio, and that is object O1. Let's see if we can select 1 unit. If I select 1 unit, the weight generated would be 10. 1 into 10, which is 10. Can I fit 10 into 70? Yes, the remaining capacity is 70. And if I select 1 unit, the profit generated would be 1 into 20, which is 20. And what would be the remaining capacity? It would be 70 minus the fractional unit selected is 1, and the weight of that item O1 is 10, and hence the remaining capacity is 60. The next in order to be selected is O2. If I select 1 unit, can I select 1 unit? If I select 1 unit, the weight generated would be 20. Can I fit 20 units into 60? Obviously yes, and hence the profit generated would be 1 into 30. So 1 into 30 is profit generated, and the remaining capacity would be 60 minus 1 into 1 unit of the object O2, which is 20, and hence the remaining capacity is 40. Let's move on and select object O5. The object O5's weight is 50. Can I select 1 unit over here? I cannot select 1 unit over here, since the remaining capacity left with me in the back knapsack or bag is only 40. 1 unit of selection of the object O5 is not possible. Hence, I come to the conclusion that I can pick only a fractional unit of the object O5 and fit into the bag with capacity 40. So how many units can I select? I can select the remaining capacity is 40, and into 40, how many units of object O5 can I select? What is the weight of 1 unit of O5? It is 50. So how many units of O5 can I select? 40 by 50 units, which is 0.8. And since it is 0.8 units of the object O5 selected, the profit generated would be 0.8 into the profit of O5, which is 60, which is 40. So this would be 30, this would be 30, this would be 20, and this would be 66. Right? So let's find out what is the remaining capacity. So 40 minus 0.8 into 50, which will be 0. So we have filled the bag to its full capacity, since the remaining capacity has become 0 now. What are the objects selected? Object O3, 1 unit, object O1, 1 unit, O2, 1 unit, and O5, 0.8 units, and I do not select object O4. So we come to the end of this solution of the fractional knapsack problem. The optimal profit generated, is the total profit generated here, which would be 66. I will just put it down here as 66 plus 20 plus 30 plus 48, which is 164. So the optimal profit is 164. The optimal profit is 164. And what are the items selected that has generated this profit of 164? The items selected are the solution vector of items selected would be object O1 with 1 unit, object O2 with 1 unit, object O3 with 1 unit, object O4 0 units, and object O5 would be 0.8 units. So this is the final solution of the fractional knapsack problem. Thank you.